Guidance for inspectors on on-stream and off-stream inspection of shell and tube heat exchangers, best practices for effective heat exchanger inspections. Introduction and Inspection Framework, Guidance, Objectives, Applicable Codes and Standards. This presentation provides structured guidance for inspectors responsible for evaluating the mechanical integrity of shell and tube heat exchangers during both on-stream and off-stream conditions. Heat exchangers are critical pressure-containing equipment widely used in the oil, gas, petrochemical, and energy industries, and their failure can lead to significant safety, environmental, and operational consequences. The scope of this guidance is aligned with API 510 for pressure vessel inspection, API 572 for inspection practices and damage mechanisms, and relevant sections of the ASME Boiler and Pressure Vessel Code. The intent is to support inspectors in understanding what to inspect, when to inspect, and how to evaluate findings in a consistent and code-compliant manner. The presentation addresses inspection objectives, applicable standards, typical exchanger components, damage mechanisms, inspection techniques, acceptance considerations, and reporting expectations. Emphasis is placed on the complementary nature of on-stream inspections, which focus on monitoring equipment condition during operation, and off-stream inspections, which allow detailed internal examination during shutdowns. By following this guidance, inspectors can make informed judgments on fitness for service, remaining life, inspection intervals, and the need for repairs or replacements. The content is designed for API-certified inspectors and engineers. But it is also useful for operations, maintenance, and reliability personnel involved in exchanger integrity management. The primary objective of this presentation is to equip inspectors with practical, code-based guidance for performing effective on-stream and off-stream inspections of shell and tube heat exchangers. One key objective is to clarify the inspector's role in maintaining mechanical integrity by identifying active and potential damage mechanisms before they compromise safety or reliability. Another objective is to explain how API 510 and API 572 requirements are applied specifically to heat exchangers, which often experience complex corrosion, fouling, and flow-related damage on both shell and tube sides. The presentation also aims to improve consistency in inspection planning and execution by outlining typical inspection activities, tools, and data requirements for each inspection type. A further objective is to highlight the limitations of each inspection approach, helping inspectors understand when on-stream monitoring is sufficient and when off-stream internal inspection is necessary. Finally, the presentation seeks to reinforce good inspection practices, including proper documentation, trending of inspection data, and effective communication of findings and recommendations. Achieving these objectives supports safer operation, optimized inspection intervals, reduced unplanned outages, and compliance with recognized industry standards. Shell and tube heat exchanger overview, typical design components, common damage mechanisms in heat exchangers. Shell and tube heat exchangers are among the most common types of heat transfer equipment used in process industries. They consist of a bundle of tubes enclosed within a cylindrical shell, allowing one fluid to flow through the tubes while another flows on the shell side. From an inspection perspective, these exchangers are classified as pressure vessels because they contain fluids under pressure and temperature. Key pressure-retaining components include the shell, channels or bonnets, tube sheets, nozzles, and covers. The tubes themselves, while thin, are critical for process integrity and can be a primary source of leaks or cross-contamination. Inspectors must understand the basic configuration and flow paths to correctly interpret inspection findings and identify likely damage locations. Design variations, such as fixed tube sheet, U-tube, or floating head designs, influence accessibility, inspection scope, and damage susceptibility. A solid understanding of exchanger fundamentals allows inspectors to plan inspections more effectively and focus attention on the most critical areas. A shell and tube heat exchanger is composed of several major components, each with distinct inspection considerations. The shell is the main pressure boundary on the shell side and is subject to corrosion, erosion, and external damage. Tubes form the primary heat transfer surface and are often thin-walled, making them susceptible to corrosion, erosion, vibration-induced fatigue, and fouling. Tube sheets provide structural support and sealing between shell side and tube side fluids, and they are common locations for crevice corrosion and cracking at tube-to-tube sheet joints. Channels and bonnets distribute tube side flow and are pressure-retaining components that may experience corrosion. Erosion, or gasket-related damage. Nozzles connect the exchanger to piping systems and are prone to localized corrosion and stress concentration at welds. Supports and saddles, while not always pressure-retaining, are important for overall integrity and can influence shell distortion. Inspectors must be familiar with each component's function to assess damage significance accurately. Shell and tube heat exchangers are exposed to a wide range of damage mechanisms due to their operating environments and process conditions. General corrosion can occur on both shell and tube sides, leading to gradual wall thinning. Localized corrosion, such as pitting or crevice corrosion, is especially common at tube sheets, under deposits, or in stagnant areas. Erosion and erosion corrosion may result from high-velocity fluids or entrained solids, particularly at inlets and outlets. Fouling can reduce heat transfer efficiency and create underdeposit corrosion conditions. Stress corrosion cracking may occur in susceptible materials exposed to specific chemical environments and tensile stresses. Fatigue damage can develop due to flow-induced vibration or thermal cycling, often affecting tubes or tube-to-tube sheet joints. Understanding these mechanisms, as described in API 572, helps inspectors anticipate where damage is most likely to occur and select appropriate inspection techniques. Definition and purpose of on-stream inspection: on-stream visual and external inspection, on-stream thickness and process monitoring. On-stream inspection refers to inspection activities performed while the heat exchanger remains in operation. The primary purpose of on-stream inspection is to monitor equipment condition, identify early signs of deterioration, and verify that operation remains within safe and design limits. API 510 recognizes on-stream inspection as an important element of an overall inspection program, particularly for tracking corrosion rates and detecting external damage. On-stream inspections are non-intrusive and rely on visual examination, thickness measurements, and process data rather than internal access. They are especially valuable for extending run lengths and reducing the likelihood of unexpected failures between shutdowns. However, inspectors must understand that on-stream inspection complements rather than replaces off-stream inspection. Proper planning ensures that on-stream activities focus on the most critical and accessible indicators of exchanger health. External visual inspection is a fundamental on-stream activity for shell and tube heat exchangers. Inspectors should examine the shell, channels, nozzles, and supports for signs of leakage, corrosion, deformation, or mechanical damage. Evidence of staining, dripping, or product odors may indicate active leaks. Insulation condition should be assessed, as damaged or missing insulation can accelerate external corrosion and may hide corrosion under insulation. Inspectors should also observe for unusual vibration, noise, or movement, which could suggest flow-induced vibration or support issues. The surrounding area should be checked for proper drainage and absence of corrosive spills. External visual inspection provides immediate qualitative information and can often identify issues that warrant further investigation or earlier shutdown. Thickness monitoring is a key on-stream inspection technique used to assess corrosion rates and remaining life of pressure-retaining components. Ultrasonic thickness measurements are typically taken at established corrosion monitoring locations on shells, channels, and nozzles. API 510 requires that thickness data be trended over time to calculate corrosion rates and determine inspection intervals. In addition to physical measurements, inspectors should review process data such as operating pressure, temperature, flow rates, and pressure drop across the exchanger. Changes in pressure drop may indicate fouling, blockage, or tube failures. Correlating thickness data with process conditions helps inspectors understand damage progression and validate assumptions used in fitness for service evaluations. Definition and preparation for off-stream inspection, internal visual and component inspection, tube inspection and NDE techniques. Off-stream inspection is performed when the heat exchanger is removed from service, isolated, and made safe for internal examination. This type of inspection provides the most comprehensive assessment of exchanger condition and is essential for confirming internal damage mechanisms. Preparation is critical and includes reviewing design data, previous inspection reports, and operating history. Proper isolation, depressurization, draining, cleaning, and gas freeing must be verified before entry or opening. Inspectors should ensure that blinds are installed as required and that permits and safety procedures are in place. Effective preparation minimizes inspection delays, improves safety, and ensures that inspection objectives can be fully achieved during the limited shutdown window. Internal visual inspection allows inspectors to directly observe the condition of shell side and tube side surfaces. Inspectors should look for corrosion, erosion, fouling, cracking, deformation, and evidence of overheating. Tube sheets should be carefully examined for crevice corrosion, ligament thinning, and cracking at tube-to-tube sheet joints. Channels and bonnets should be inspected for corrosion patterns and gasket surface damage. Internal inspection findings provide critical confirmation of damage mechanisms inferred from on-stream data and often form the basis for repair or replacement decisions. Tube inspection is a major focus of off-stream inspection for shell and tube heat exchangers. Common non-destructive examination techniques include eddy current testing, which is effective for detecting corrosion, pitting, and cracking in conductive tubes, and ultrasonic-based methods such as IRIS for accurate wall thickness measurement. Tube inspection data are used to assess the extent of tube degradation, determine plugging criteria, and evaluate remaining life. Inspectors must ensure that inspection coverage is adequate and that acceptance criteria are clearly defined. Proper interpretation of tube inspection results is essential for preventing tube leaks and maintaining exchanger performance. Fitness for service and inspection intervals, documentation, inspector competency, and summary. Fitness for service evaluation is used to determine whether a heat exchanger can continue operating safely with identified damage. Inspectors compare measured thicknesses and observed damage against minimum required values derived from design codes and API 510 criteria. Corrosion rates calculated from historical data are used to estimate remaining life and establish appropriate inspection intervals. Risk-based considerations, such as consequence of failure and likelihood of damage progression, may also influence inspection planning. Applying fitness for service principles ensures that decisions are technically justified and consistent with industry standards.